director of the Institute of Digital Humanities from Anchor University, Nigeria, and he holds a Bachelor of Arts degree in English and Education, a MED in Education, a PGD in Computer Science as well, and a Master's in Computer Science and a PhD in Computer Science. He is presently a senior lecturer in the Department of Mathematical Sciences and the acting director and of the institute, of course, uh, of the Anchor University, Lagos, Nigeria. He has published 60 research papers in reputable journals and conferences. We highly welcome you, Doctor. I'm going to stop sharing my screen so you can share your screen.
Audible to all of us now. Can you hear me?
We hear you well, sir.
Very good. All right, so today I'm talking on stochastic process of the African buffalo optimization algorithm. And as a way of introduction, let me talk just very briefly on the issue of optimization. What is optimization simply? It is a way to get the best results using the least input. And today is a very common consideration in science, business, and engineering designs is the issue of costs and serviceability, thus highlighting the need for optimization. Just as businesses are concerned with maximizing profit, so also engineering design organizations are concerned with continually maximizing the efficiency of the design products, and scientists are engaged to obtain better results with less input of time and materials. Now, all this highlights the need for optimization and is at the heart of decision making, both in manufacturing, industrial concerns, etc. So, with that in mind, may I also emphasize that optimization is relevant in virtually every field of human endeavor, ranging from medicine, pharmacy, science, engineering, to business management. In fact, to overlook optimization is to put your business concerns in jeopardy. That is why this area is a very favored area of research in the last 50 years. All right, so now, simply put, I'm saying that optimization is concerned with discovering the best solution out of several feasible solutions. And it could be discrete or it could be continuous, depending on the problem that is being solved. In all, it is safe to say that whether in continuous or discrete environments, the overall goal of optimization is to either minimize or maximize a function. In other words, optimization can be said to be the economics of science and engineering, with the aim of minimizing costs and maximizing profits. All right? And in the aim also of trying to minimize the time input of industrial procedures. All right, now let me talk also very quickly on the issue of heuristics and meta-heuristics. In some fora, they are used interchangeably, but that cannot be the correct situation. What are heuristics? Heuristics means having to exploit information about a given problem to get a problem solved. So my capacity to exploit some information about a problem helps me in order to bring about solution to that particular problem. So the use of heuristics enable algorithms to obtain quality solutions to difficult optimization problems at a reasonable time. But on the other hand, meta-heuristic algorithms employ some local search in addition to global exploration using randomization. So what we must understand about meta-heuristics is the fact that it must involve some elements of local search. It must also involve some elements of global exploration. And number three, it must involve some randomization because in general, meta-heuristic algorithms are stochastic in nature, meaning that with each run, it's expected that you obtain a different result. And that is why meta-heuristics has wider applicability than heuristics. All right, heuristics usually are designed to solve a given problem, as opposed to meta-heuristics that has a wider applicability because it makes use of local search, global search, and then randomization. So as saw today, in this area of research, meta-heuristics are more popular, and almost every year now for the past several years, we have been having some new ideas, some new algorithms being designed. Now, here I have, I don't know how clear that this is, try to just to a taxonomy of algorithms in terms of what are they. Talk about algorithms, we are asking that is either a stochastic algorithm, which I explained a while ago, or it is um, it is an exact algorithm. It's either stochastic, meaning that it gives, is not promising you a correct answer, the exact answer, but it's playing around the answers. So it's playing around on the exact answer, or it could be deterministic, meaning that it is exact. All right. So I don't want to go into that because today our major concern in this session is talking about the stochastic process of the African buffalo optimization algorithm. Now, this animal in the screen is what we call the Cape buffalo or African buffalo. Now, we also have the Asian buffalo, that's why we call it African, all right? And there's a little difference from them. The Asian buffalo are more or less water buffalo, all right? They play around water, stay around water a lot. But this one stay more on land and so does more extensive grazing. And so in this algorithm that we did a few years ago, we paid attention to the African buffalo because of what we want to achieve. Because they move more on land, so the African buffalo had a larger herd. In fact, you can see a herd of buffalo that is up to about 1,000 buffalo strong, moving at the same time and grazing at the same time and communicating with one another as they are
Sir,
grazing.
I guess
Now,
we don't have your voice.
hello?
Uh,
Hello?
I guess
Yes,
there
ma'am?
was an interfere. No, I don't hear you. I'm not pretty sure. Does everyone have the same problem, or is it only?
Okay, can we find out from others? Are you hearing my voice? Is it clear enough?
Yes, yes, yes. We hear you.
It's okay now. Oh,
Great,
good.
great.
Thank you.
Sorry, maybe it
All
was
right.
my problem.
All right. Thank you. All right. Thank you. All right. So let's move. Now, in designing algorithms, there's always a process. And so here on the screen is a flowchart of general algorithm design. First thing that happens is the first step is that you study the swarm. If you want to design a swarm optimization algorithm, the first step usually that you study the swarm or the nature-inspired item that will form the basis of the algorithm. In this case, the African buffalo optimization, the African buffaloes. So what we did in this is that we have to study the buffalo, study their migrant behavior, study their communication skill, study also the working of their brain. So how does the brain of the buffalo work? And from our study, we came to understand a few things, all right? We came to understand how they move, that the African buffalo basically has two sounds. It makes just two sounds. One is the wah sound. We have published a lot of about 100 publications on African buffalo so far in the past few years. All right. So it makes use of the wah sound and two, the ma sound. The wah and the ma sound. Now, the wah sound, how does it operate? The wah sound is used to ask to tell the animals that look, you can explore. Why? The environment is safe. The environment is conducive. So you are free. So you relax and graze as much as you can. All right. And then the ma sound, the one is wa, explore. All right. And then the ma sound is asking the buffaloes to come together. All right. Because let me mention this, because it may interest a researcher, that this is the African buffalo is one of the very extremely few animals that are democratic. Now that sounds interesting. In fact, that's one of the things that excited me about this. That even though they move in a herd that runs into several hundreds, sometimes up to 1,000 strong herd, that these animals have the capacity to conduct an election. That was fantastic. All right. So in their movement, they want to find out after a period of that's when they're in a location, which is synonymous with local search. All right. That when they want to move, they call the whole team together. And when they're in they want to conduct an election to determine where do we go? We go east, west, north, or south. All right. And this is very unique because it makes them, in fact, they are about the largest grazing herd on the earth today. Elephants graze also, but you cannot find 500 elephants in a place. It's not possible. Not even 100. I can't remember in literature of any situation of having 100 elephants together in one place. But this animal, this the African buffalo, which is to be able to have up to 1,000 and they graze together. So they become effective grazers because of their capacity for democracy. All right. Now, how do they do it? When you watch it in Nigeria Wild, which is a television channel, right, watch in many countries of the world, you discover that they are staying together. One of them will just get up, look at a particular direction, and then stoop again. And that one is wonderful to watch them. It's wonderful to watch their election. So one city just get up, look maybe to the east, sit down, and that one may get up, look to the south, sit down, and they go that way. And by the end of the day, you discover that in many of the instances where many of those animals look towards is where the whole herd will follow. That's fantastic. All right, so let's quickly move for time's sake. So we study the animal, and then next thing you do, you develop a mathematical model that represents their organization. Number 4, you develop an algorithm. Number 5, you test the algorithm on some certain case studies, discuss results, and finally draw conclusions and make recommendations. So let's go. So let us now to pay more attention to the algorithm, the African buffalo automation algorithm. Let's see how does this one work. Now, in our screen is it. So first step here is about 6-step algorithm. First step, we initialize the buffaloes within the search space. Next, we calculate the buffaloes of exploration, and which using that equation there. And then next, we now calculate the buffaloes locations using the equation 2. Next, we determine if the best buffalo, the one that is nearest to the optimal result, is updating. And if it is, we proceed to the next step, which is step 5. But if it's not updating, after 10 iterations, then we return to step 2. Then next, we cross-check the stopping criteria. If reached, great. But if not reached, we'll go to step 2. But if reached, we'll go to step 6. And step 6 is that we simply output the solution. All right, now, so this is the flow chart. I've explained this while talking a while ago. Initialize, update. After 10 iterations and there's no result, you return to re-initialize, and then you check the stopping criteria. If it has reached, then you output the result. But if not, you go again to re-initialize the buffaloes. That's the way this algorithm works. All right. Now, in this address, I'm trying to physically show how this algorithm works. Not from a machine perspective now, but this is from a human perspective. Now, and this is the motivation of this research, and this is its novelty. Now, if you go to literature, there are very few works that you can find of a tutorial in an algorithm that is given from a human perspective. Most of what you may find is giving this tutorial from a machine perspective. That does not give us the correct, the true picture. All right. So what we intend to do, and let me just say that this work has been published. We published a work on the stochastic process of this algorithm, and you can find it maybe in the reference, scientific reports. All right. All right. So how does this work? One, to solve a global optimization problem. This algorithm works in this way. It employs 7 steps. First, we select the buffalo. Next, we select the parameters, because this algorithm, fine. Another great thing about this algorithm is the fact that it has just 3 parameters. So this makes it extremely fast when compared to other similar algorithms. Just 3 parameters: 1, the pi, the LP1, and LP2. All right. Now, so we decided in a way that you can even use our earlier parameter that we obtained from after an extensive search. And so in that case, it becomes like a parameterless algorithm. That's again, and that's strength of this African buffalo algorithm. All right, so next step 3 there, we update the buffalo's exploitation as they were wild sound, and then determine the prevailing best buffalo. BP there is best buffalo, all right, for each buffalo. So what is the best position for each buffalo? And the BG, what is the best global position? And that can be done using equation 1. And then from the result of equation 1, we go to equation 2, and then we verify if the best global buffalo, meaning that the best buffalo in the entire herd, 500, 800, 1,000, as the case may be, all right, is this still updated? If yes, we proceed to the next step. If no, we turn to reinitialize. All right, and don't forget we said 10. 10 is found to be a good number or of iterations of if each time there are 10 and it's not updating, then we have to go back to reinitialize, and then we output the best result. I hope we are following. So to end this, to conclude this presentation, we want to check the ABO as the algorithm, the African Buffalo Optimization Algorithm, the ABO, on a 2-dimensional search space. So this is a shear simulation, all right? Because we're bringing out the human perspective to it. So how does it work? First, in our simulation, we assume we use 3 buffaloes, all right, to make it simpler to calculate so that everyone can follow. So we call it buffalo K, buffalo L, and buffalo J, so JKL. And we assume that buffalo K is in location 7, 9, meaning longitude 7, latitude 9. Buffalo L is in location 11, 15, longitude 11 and latitude 15, and Buffalo J 4, 15. Again, we assume that the global optimal point for this problem we are solving is 41.5 stroke 75, so longitude 41.5, latitude 75. And in the first iteration, we put the 3 parameters as 0.6, 0.5, and pi being a random number, actually lambda. Lambda being a random number is any number from 0 to 1, which is consistent with any other swarm optimization algorithm in literature. It's important to observe that the lower the value of lambda, the more the exploration, and vice versa. So please know this. When you use this algorithm, understand this, that the lower the value of the lambda, which is a randomization number, the more the exploration. And the higher the value of lambda, the more the local search. All right, so let's move. So from what we're doing now, these are what I said now. Buffalo J is location 4/15. Buffalo L, that's BL, is 11, 15. And Buffalo K is in 7, 9. All right. Longitude and latitude. Please take note of that. All right. That's just basic geography. All right. So this is where they are. Now, plotting our algorithm to solve this given problem. This is what we arrive at. All right. So don't forget that the BP is the best position of each individual buffalo. The best position of each individual buffalo. So we assume right now that we assume for this simulation that where they are now, their initial point of starting definitely become their best starting position. Okay, and so we just took one of them, the position of Buffalo J, which is 11, 15, that is picked randomly. We pick that as our global best position. So plotting the algorithm, because don't forget, we have 2 equations, which is the first equation, MK plus LP1 BG minus WK plus LP2 BPK minus WK. Now, what is the K there? The K is Buffalo K. All right. So please let's take notes. Or is there any question? Any question? Feel free to ask me. All right. So for this algorithm, why it's so simple is that there are just 2 equations that control the movement of the entire buffalo head, and that is the Ma equation MK, and we'll see later the Wa equation WK with respect to Buffalo K. Because remember I said we already have 3 buffaloes, Buffalo J, Buffalo K, and Buffalo L. All right. So plotting what we have said about their locations into the graph, we get this, that the best position for MK prime, which is the first movement of the buffalo, come to 9.4. All right. And then solving it again in a second, the longitude at 9.4, latitude come to 12.6. I hope we are following us, because it's quite interesting. I want to follow it. And if there are any questions, feel free to reach out to me later on, or simply go to our work, our published work in scientific reports published by nature.com, and then you will get it. And it's quite interesting. It's quite interesting. All right, so let's move. Let's move. All right, so at this point, is it moved to 9.4 longitude and latitude 12.6. Now, to check the next movement, we have to plug this into the movement equation. The movement equation is a Y equation, which is the exploration equation. Recall that the local search equation is the MA equation that begins with MK prime. And while the other one is the movement equation WK prime. The MA local search MK prime and the exploration WK prime. All right. So now, with the value we obtain from the MA, which is a local search, we now plot it into the WK. We refer to Buffalo K. And so what do we get? For the longitude, we get 43.2. And then for the latitude, okay, longitude, we have 32.8. And for the latitude, we have 43. When I'm through, ask your questions. All right, so let me continue then. Okay, so now with this, we have Buffalo K. Then we do the same also. So we update using our new information. And then we also do the same for Buffalo J. And when we do that, plotting our values into Buffalo J, then what we have? We have that the longitude comes to 8.2, yeah, 8.2, all right? And then the latitude comes to 21.6, highlighted, 21.6. So the new location for Buffalo J now came to 8.2 and 21.6. All right, so we'll do the same thing. So then, having now gotten the MA value, we plot the MA values into the WA value. Remember, the MA value, local search value, and the WA values is the global search value. All right, and the WA value is what tells the buffalo to move to a new location. The MA value is concerned with exploitation. So hold on, stay here, Grace, this is good. All right, so plotting that value into the movement location, the WA equation, then we come to new values for Buffalo J. So we now come to 13.56, yeah, and then 40.67, which will now, so the new WA location of Buffalo J comes to this 13.56, and that's longitude 13.56, and then latitude 40.67. All right. So having done now for those two, we're not going to the last buffalo. We're dealing with three buffalo: Buffalo J, Buffalo K, and Buffalo L. So Buffalo L also following the same procedure. All right. We now have the longitude movement now coming to 6.8, and then the latitude coming to 15. All right. So the new location for Buffalo L become longitude 6.8 and latitude 15. That's 15. All right. Now with this, we now also go to check what will now be its WA value. So plotting the location we just got it now to our equation, then we have that the WA value become 22.25 and 37.5. Okay, now, so having obtained this, so could mean that the animals have made their first movement, but in their first movement, they were unable to arrive at the optimal answer. They've not arrived at the optimal solution. So what we do now, we now go to the next iteration. All right, using the correct the present values as already obtained, we now plot for Buffalo K, or that's MK double prime now. So you can see that MK double prime. So double prime is simply saying that it is the second movement. First prime, first movement. Prime, the second. Working on that, we now get latitude 9.4 for MK and longitude 12.6. So MK prime now gives all this answer. MK prime now gives us 9.4, longitude 9.4, and then latitude 12.6. What we have to do next, we have to look for the Y value. How to look for the Y value. And what we do, we just plot our 9.4, because the Y value is WK plus MK. And what does it give us? It gives us 20.87, and then the latitude comes 28. So the current location now becomes 20.87, 20.89, and then 28. So longitude 20.89 and latitude 28 is the present location of the buffalo. All right, so that is for Buffalo K. We do the same thing for Buffalo J, because there's not a movement. So we show it forth now. There's not a movement. The second movement, the first movement is shown with the blue arrow. Second movement is shown with the red arrow. All right. So having done that for MK, we'll do it now for Buffalo J, and that gives us this for the mass location 16.01, and then longitude and latitude 17.79. And then what we do next, we go and check for the exploration value. The exploration value. And that gives us, plotting again that value there, we have 36.96 and then 65.58. So which means that Buffalo J has moved from where it was now. It is now in location 36.96 and 65.68. All right. So we do the same thing for the last buffalo. We are rounding off now. Last buffalo, Buffalo L. And doing that for Buffalo L, we have this for the mass value 7.49, and then for the Y value 20.67. All right. Then, as usual, using the mass value, we plot for the Y value. Remember again that the mass value is the local search value, the exploitation value, and the Y values are the exploration value. So plotting the mass value into the Y value, we have 41.5 longitude, and then latitude 75. So at this point now, the ABO verifies the exit criteria and discovers that this has been met, since its assignment is to obtain the optimal result, which is 41.5 and 7.5. And this was discovered by Buffalo L. So the ABO attributes its result at this very point. Like I said, this is a paper published on this. If you want to get more details, just go to this paper and you will get more details. Thank you very much. I have to close a little earlier because I want to give you sufficient time for questions. So please, are there any questions? Feel free to ask now.
Thank you, sir. That was a very, very informative presentation. We thank you for your time and your presence in our webinar.
My pleasure.
Let me see if there are any inquiries. Fred says, nice work. energetic and enriching presentation from Dr. Alexander. He thanks you for the super knowledge shared. We also thank you too. And the inquiry here is that what is African buffalo optimization?
Pardon? Again, what's the question?
I repeat that again.
Hello?
Uh,
Please do.
hello, is my voice audible to you right now? Do you hear me?
Excuse me?
Uh, I'm sorry, it got interrupted again. What is African buffalo optimization?
Okay. Yes, it is an algorithm that can be applied to solve diverse problems. So it is a swarm-based optimization algorithm. Now, an algorithm is like a formula in mathematics, all right? So it is applied to solve diverse problems. So far, this algorithm has been applied to solve diverse scientific, engineering, and industrial processes. In fact, I read a paper where it's applied in building a nuclear power station. That research paper was done in Iran, all right? Somebody, a particular researcher, is applying this algorithm to solve or to build a nuclear power station, and it has capacity. This algorithm also has the capacity to fly an aeroplane, you know, on autopilot. Is able to pilot because tapping from the migrant attitude of African buffaloes. African buffalo is simply an animal of the size of the same family with the domestic cow. All right, I'm sure many of us are familiar with cow or cattle. Yeah, so that the cattle is the domestic equivalent of the wild type. The wild type is the African buffalo. That's a wild type of it. But the home type is called a cow. Now, so these animals are so intelligent because this is a work on artificial intelligence. So they're so intelligent that they are able to tell where, because they feed on grass, they are grazers. So they're able to tell that at this point of the year, it's very likely that there will be rain in this location of our movement space. So they will all go there. Now, African buffalo have the capacity to travel the whole continent. All right. So it's able to properly estimate without they take lots of water, up to about 20 liters per day, and they eat lots of grass. Okay. So they're able to estimate when this abundant grass they eat is in a location. Now, in Africa, generally, we have two main seasons in Africa. We have the rainy season, where rain falls a lot in some areas. But the way it is that when rain is falling, for example, a lot in West Africa, it may be very dry up north, and vice versa. All right. So these animals are so intelligent that they're able to tell where are where is rain fall, because rainfall likely will give birth to fresh green grass, and that is their delicacy. All right. So with this, we drew intelligence from these animals, and then we are now able to use to solve diverse problems. But personally, in my research, I used to solve global optimization problems. I use this algorithm to tune the parameters, the PID parameters of an automatic voltage regulator, and the result was excellent. Very good results. We also applied it to traveling salesman problem with very good results also. And have been applied to diverse, just Google African buffalo optimization algorithm at the end of this presentation, and you see, all right, that applied to diverse areas, and that have been so good. Why? Because of this democratic capacity. Also, whatever you are taking, they are taking the best because that They are harnessing the brains of the individual buffalo in solving their problem. Thank you.
Thank you so much, Doctor, for answering the question. I shall, apologize for not answering the other inquiry because we don't have so much time. But of course, you can ask the question via email. Of course, we really appreciate your time and presence in our webinar, and you really graced our webinar with your presence.
Thank you very much. I appreciate it also.
Yeah. Okay.